Okay, getting started once again. I've done, I guess this is my third or fourth video for the day. I've done some on Microsoft Teams because I had a master's student do his project defense, which went really, really well. I was really happy with the way that worked out. And Teams works, maybe the video with Teams is better than it is here, I don't know, but I do like Slack, the way it works for the entire group of my students at least, and hopefully you're liking it too. One of the features I'm really starting to like is the fact that you can just push stuff at me on Slack, no matter the file size, and it just gets to me and I can pull it down and then store it away where I need to store it. And my master's student had files in PDFs that were like 27 megs, and Slack didn't have any problem letting those go on and then getting pulled down. So that should be the way everything gets shared back to me on your direct messaging channel. So what's new is I did post up the solutions to number 8. I fixed the solutions for quiz 9, and yes, we are out of sync and we'll stay that way till the end of the semester. The homework assignment number and the quiz number are never going to be the same again, I don't think. So get used to that. But I did have to make a change in number 9, and I discussed that in the solution, so please look at that. I got my brain wrapped around thinking about harmonic number, and the harmonic number was 6. It wasn't 2 like I was thinking. It's 6 kilohertz is the the sixth harmonic of 1 kilohertz. So that was the major change that I had to make in that solution. So that's the one that's up there right now. No new assignments, of course, since that's all fixed. We do need to spend time, and I guess we'll do that right now when we jump over. We do need to spend time on making sure we know about the exam. So when Set 9 went up last week, I had this little topic for discussion in here, and we've talked about this twice since then. As I look at my calendar again, I see the 23rd is the earliest. I'm probably most comfortable with the 28th or the 30th, with this first week in May being the last week of regular classes. So I guess my question again is, does anybody have a preference on those dates? Chris is usually a vocal guy, but he's not here. So you are here. So you are going to be vocal, which is okay. No conflicts? There's always conflicts. Yeah, that's right. Second project will be easier, but yeah, you're absolutely right, and that's my concern as well. Does anybody else want to chime in, either on Slack or just speak into their microphone? There will be a review day, and it will be, on Thursday then, a week from this Thursday. So you could care less? You do care though, right? Okay, here's something else that comes up when I pick a date or any date is, and remember I talked about this 2 weeks ago, being able to print something, because what I will do is I will push it onto Slack. You will grab it off of Slack as a PDF, and then you have to print it. Or people like Chris that have a tablet will probably just fill it out on the PDF, but if you don't have a printer, then we have a problem. If you do have a printer, we still have a problem, because then you have to get it back to me somehow or another. So you have to be able to scan it either with a scanner you might have at home, or by taking nice pictures with your cell phone using some app like Adobe that helps you line up the pictures and so on. So I'm thinking maybe on this Thursday I'm going to do something silly, but I'm going to have another mock quiz, and I will test your ability to get the document back to me in a readable form. So what I'll do is I'll let you print the print the quiz, scribble on it, take notes on it or something, and then I'll put it up before class starts, and then I'll just have you get it scanned and sent back to me just as a test that you can make that happen. Yes? They're okay. I mean, you've done Word the last 2 times, and I prefer you to have Word exported as a PDF because I have to give you... Yeah. I'll take a look at them again. They seem like they were okay. The last step is what I'd like you to take care of for me. And that way I just label everything. I label everything with a standard notation that I kind of established when I gave your exams back. And some of you are really on board with that, so I don't even have to rename it. But at any rate, I just want to see that we can make this work, because the plan will be I'll get it up there early. We'll start class. I'll walk you through the exam. My preference would be, while you're working the exam, to just keep your video running, so that way if there's questions, I can take care of them and feel like everybody's, engaging. It'll be an open book exam. I won't be able to limit that anyway. I mean, I want you to obey an honor code, obviously, and not be talking to each other. And I would rather that you write out your own crib sheet once again, because that will be a lot faster than trying to go through the book. I really don't recommend that at all, but, if that's the way you want to do it, that'll be your choice. But then we'll work it through down to the end, and then I'm going to give you, a small amount of time to get it wrapped up, scanned, photographed, whatever, and get it back to me. And then I will set, then it'll be over with at that point. So does everybody like the idea of a little practice on Thursday, just so we can see if we can go through the motions? Okay. It gives me confidence that everybody kind of has a routine down, because I've had to grade homework that's been photographed with a cell phone, and it's very difficult to read, and I'm not really enthusiastic about having something that's really of low grade quality. So yes. No, yours are perfectly good. I think you have a flatbed scanner though, don't you? Okay. Yeah, I want you to do it Slack, because yours comes out fine, and I have an app on my phone that helps line up and takes care of that skew that you get, right? You get skew very easily, and there's now image processing apps that help with that skew problem. That's the most important thing, and then sometimes it's faded, but this way I'll have an idea, and that way I can critique anybody that's on the weak side. Okay, so I'm going to keep moving at this point, and what I want to do is just see what questions you might already have. There's no phase lock loop question on here, so that's why I want to just do this first and have this behind us. One problem is very easy, and one problem requires some nice, well, I guess the last problem is a phase lock loop problem. We'll hit that pretty early on. It's not one that you turn in though. Problem 426 is a lock steady state phase error problem for a first order phase lock loop. But of the two problems, number 3 there is pretty straightforward. That one revolves around Carson's rule, and I think in my hints page down here I pretty much give you the strongest hint I can possibly give you, and that is that this version of Carson's rule is how you want to think through this problem. This came out of another book, but I like the problem. I think it's kind of a cute problem. Cute in the sense that it's looking to trip you up. Whenever you see the word fallacy in an engineering context, you have to think, I'm going to be confronted with that someday in my career where two of us don't agree, and you're going to have to beat this out and come up with who's got false thinking going on. So I can just imagine two people arguing about this, maybe not violently, but they'd be saying, this is right, no, this is right. And then they go to the spectrum analyzer, put the signals in, and they see what the real result is, or simulate it in Python or something. So I like the problem. It's really very, very easy, but it just makes you have to pause and think a little bit. Second problem, though, is a little bit more involved. It could be viewed as a circuits problem or a nice little analysis problem. So I want to spend a little bit of time on that, giving you some ideas. Has anybody looked at the problems and want to ask me about anything more about number 3 there, or number 4, which is from the book? If not, I'm going to... Okay. Do you think you'll get on lost if you start spending more time tuning in? Okay. Perfect. Well, I'm going to help you tune in a little bit more to problem number 4 right now. So problem 4 is a circuits problem, but it's a systems modeling problem. So remember, in the notes we talked about a slope detector for frequency modulation. You could send an FM signal through a filter that would have a slope in its gain response right over the FM signal. So normally you think of a filter as being where you want to center the signal on the pass band of the filter or inside the bandwidth of a low-pass filter. But in this case, we're looking to have an approximate linear change in gain of the filter right over the carrier frequency that's been FM modulated. So we're trying to get a conversion from frequency deviation to amplitude fluctuation, and that's the application here. The example I did in the notes was with a high-pass filter, and I'm going to jump back into the Jupyter Notebook to explore that and give you some techniques that will be useful on this problem. The problem, though, in the book is a bandpass filter. So actually, you have to study it to know that it's going to be a bandpass filter. But at any rate, just to sketch out the filter, it's a series RC tank, and then it's got a load resistor on it, and then it's followed by an envelope detector. So you've got L, C, and R, and the component values are on here for everything. 10 to the minus 3 henries, which would be 1 millihenry. 10 to the minus 9 farads, which would be 1 nanofarad. And then R is 1 k ohm. And you're going to be putting an FM signal in here, so he calls this XR of t as in the received signal. And then you're interested in what the voltage is out over here, so he calls this E of t, as if to say that's going to be envelope detected. I guess that's why he calls it E. At any rate, you can assume in the modeling here that the impedance looking in there is infinite. So you don't have to worry about any loading from that circuit. So really, the problem just boils down to solving this in the S domain and then getting the frequency response. So that is the way I would write this out. So you're going to want to get the frequency response from the input to the point at E of t. So you're just going to find a system function for this. So you're going to end up with h of s equals something. So you're going to end up with a ratio in here, right? And it's a voltage divider, if you want to look at it that way. So you're going to use your circuits theory to do that. And like I said, I would solve it in the S domain. And then I actually solved it symbolically first. So you'd have R, and you'd have R plus, and you can fill in the rest of that. But you know how to do that, right? Everything's in series, so you're just going to be adding the impedance of L in series with the impedance of C, and then using the voltage divider idea, that's why you've got R on the top side, and then you have to have the total series impedance all the way around the circuit in the denominator. And then, of course, you'll let S go to J2 pi F, and then you can write this, then you can put in component values, or I'm just looking at my solution I've got on my other screen here. I put this in one code cell in the Jupyter Notebook just so I could analyze it. And let me just see if this makes sense. I just picked a range to sweep over. I'll just give you a hint there too. I ended up sweeping I went from 1,000 to 400,000, and then I took steps of 200 hertz, and I plotted it linear. So I plotted linear in frequency and amplitude. So it's just going to, I'm going to be plotting the problem doesn't specifically say that, but that's going to be the best way to go. So plot frequency axis linear and plot magnitude of h of J2 pi f. So you just want the magnitude. We don't want it in dB. We don't care about the phase. We just want to know what the magnitude response is versus frequency. And you're going to get some kind of a, like I said, kind of a bandpass looking filter response out of this. That'll be the transfer function from the input to the output. And then you have to decide, and this is a design problem, so this doesn't have any one correct answer. You have to decide where you want to center your carrier frequency. So you have to pick choose where you want FC to reside, and then you have to delve into what's going on inside the filter, what's interesting about the response. Once you pick FC, then you want to see what is the slope in the neighborhood of that FC, of the magnitude response. So you're going to want to characterize the magnitude response and look at its slope, let's say, and you're looking for a flat spot in the slope, because that'll mean that the gain change versus frequency is approximately constant over some band of frequencies. So I'll tell you right now what you can rule out. And if anybody wants to jump in with some ideas to share them, I'm listening too. You don't want to pick where the peak is. I mean, I didn't draw it that accurately, but the peak is not going to be the flattest spot. If this was the actual shape of the filter, though, candidate regions might be just the way I've drawn it. It looks like it's kind of flat in there. Looks like the slope is kind of constant in there, and it looks like it's kind of constant over here. But this is not at all the exact shape that you're going to find, but that's what you're looking for. You're looking for a region in the gain magnitude that is got a constant slope over the widest band of frequencies, because then you know you can put in an FM signal, like if the FM signal was going to go reside in here with all of its sidebands, suppose that was where FC was, then the frequency can deviate back and forth and the amplitude will move up and down in a linear fashion relative to the frequency deviation. So that's what you're looking for. Does that make sense? No one wants to comment. You can Slack a message to me too. So, and that's what the problem statement says. I mean, I'm just going to go read the problem. It says, plot the magnitude of the transfer function. From this plot, determine the suitable carrier frequency, and then the discriminator gain constant, Kd, and that would be the conversion of frequency to amplitude. And then estimate the allowable peak frequency deviation of the input signal. And that's a guesstimate on your part. So like I said, it's not, no answer is going to be identical. It's kind of taking a shot at designing something or working with some component. But here, I would kind of look at, in this example, if that was a linear segment where it was pretty constant slope-wise, I would say that is my total good region, and then the peak frequency deviation can move from the center of that band up and the center of that band down. So the peak frequency deviation would be that bandwidth divided by 2. Sound okay? So I'm going to now take an example in case in point. I'm going to go back over here to the example we were looking at in the notes under slope detector, or in the notebook, I mean. Here I took a Butterworth high-pass filter, so this is a different kind of a shape, but I have a Butterworth high-pass filter, and you look at this, I plotted it, gain, not in dB, but just linear, frequency linear. So you look at this and say, where is the best place to put my carrier frequency? Well, it's kind of hard to tell. It looks nice, like a very nice constant slope, but in reality, you don't know that until you do what? What do you have to do to figure out what that slope is? Versus, you could zoom in on it, but what do you use from calculus? Okay, so we have a cool operator in Python, a discrete derivative called diff, and diff is just going to take a value minus the previous value all the way across an array. MATLAB has a similar function. I think it goes by the name diff as well. Because to take a difference, you're going to use up, you're going to have one less point as a result of taking the difference because you're doing it pairwise. When this function returns, it has one less value in it than it did when it started. So if I wanted to plot the diff versus frequency, I have to make my array one value less, and that's what I'm doing here. I'm going to plot the entire frequency range from the index frequency at the index 0 up to 1 less than the top value. And then if this is going to correspond to the derivative, I need to divide by, I did that wrong. In this case, in this particular problem, I stepped the frequency by 10 hertz. So if I was taking the derivative involving a discrete derivative, I would take the difference pairwise between all the points, and then I have to divide by the delta f, which would be, in this case, 10. So there I'm normalizing it so it is like a numerical approximation to the derivative. So then I plot it, and it's a pretty small number, so maybe in the end I'd rather scale this to millivolts or something. So maybe I decide I'm going to multiply by 1,000 in the end, so I get it in millivolts. So I'm kind of back to where I was to begin with, because I divided it by the delta F value. At any rate, this is going to be where the derivative has a slope, or it's an inflection point, right? The slope is actually changing sign at that point. It's going from increasing, which is down below here, to now it's decreasing, and it's going to go back to 0 again after it goes negative. So I get this plot, and if this is the filter I had to work with, and by the way, the homework problem works out a lot nicer than this. This is a very peaked response, so there's not going to be a very good band of frequencies that we could use in here. I mean, I could make it look nicer if I was to go X lim and work around that area from, say, 6,000 to 8,000. It looks nicer because now it's a little bit flatter. Maybe I should go 6,500 to 8,500. I don't know how that's going to look. There. Then I could put the grid on that if I wanted to. So if this was going to be my discriminator, I would say I want to know where that peak is, and that will correspond to where I'd like to put my carrier. And then I'm going to say, well, it's not perfectly flat like I was hoping for, but it's not too bad. And I just guesstimate a band of frequencies where the amplitude or the slope doesn't change by that amount. It might be 10% change in slope, and you'd say it's no good after that, or 20% or 5%. It just kind of depends on what you think. In this homework problem, it's a lot flatter than this, though. So how can I find out what that value is? Well, you probably remember in MATLAB there was a function called find. Python doesn't have a find function. It did for a while, and then they did away with it. They had the find function, I think, to copy MATLAB, but then they decided to go back to their primitive, and it's called ravel. So ravel is the name of the function, and if I hit Shift Tab in there, it tells you what ravel does. You can put a condition inside of the argument of ravel to have it return where some condition is true. So I'm not as fond of this function as I am the find function, but so I get to put inside of this, I want the derivative, and this should be divided by 10. I want where the derivative is equal to the maximum of the derivative. So I'm just finding this curve, and then I'm going to set it equal to where is that max occurring. And I know it's going to give me just a single point, but to make sure I get values that are legit values, I put the operator non-zero in front of this. And then normally what I'd have to do after I do that, I'm just going to comment this out for the time being. Oops, I didn't want to do that either because that doesn't tell me anything. It's going to give me the list of values, and right now I'm getting 0 because I didn't make that divided by 10. So in this case, it's telling me that there's an array that contains one value. And that value is index 742. If I want to get that exact value, in other words, index into that array of one element, I would add one more set of square brackets on there, and now I'm going to get that exact value. So I do that, and now I know what that index is. It's 742, and I go to my frequency array and plug that index in. And what did I do wrong here? 742. Oh, I've got to put IDX max up here. Then it tells me it's 7420. So now I know with confidence that that's where I'm at. So if I wanted to just indicate that up here, I could do a little plot of that. It would be 7420, 7420, and then I would let that range from 0 up to 0.3 or something like that. And then put a red dashed line there. So I'll go red dash dash. So I have that point marked right there, and then I could play around with this a little bit by looking at this now. Is this slope is going to define the bandwidth where I want to be able to operate in, where the slope doesn't change, deviate too much, because it's going to introduce distortion or a nonlinear distortion. But I could, like I said, I could find out where this drops to by 10% or something like that. And I'm just going to look at my solution to see how I did it. I used techniques like this. And then, of course, I need to get the discriminator gain constant, and I kind of already have that right here because this is going to be volts per hertz, because I've divided in order to get that value right there. I could plug that back into the derivative operator and find out is exactly 0.3 or something closer. At any rate, I'd be able to get that out, and that has units of volts per hertz because I'm dividing by hertz, and that absolute value is a gain, which is like a voltage in gives a voltage output. So is that kind of making sense? I know you're going to have to simmer on this problem a little bit to think about it, but that's about all there is to it. And if you don't like using Python and you'd rather use LT-SPICE, you could certainly model this in LT-SPICE in a circuit analysis program, but I like staying in Python because then I can do things with the arrays that I have, like do the stuff down here. With SPICE, you'd have to use some of the operators that it has, and it can differentiate discretely the absolute value or the magnitude, but I like this better. And that's all you have to do for the problem. You have to answer the individual questions. If you were exotic, you would try to put an FM signal through there and just see how well it does at recovering it, but that's not something that you have to do. In this problem, that's exactly what I did, though. I went down below here and I did pass the signal through the high-pass filter. And let's see, I didn't define that, run that cell, didn't run this cell. I put the signal at 7,000, and now that I've analyzed it in more detail, I know that I should be putting it where? I discovered that the optimum point was 7420, right? So I should be putting it in at 7420. Run that. This was the picture that I made of it. So that's the FM carrier at 7420. And then I passed it through the high-pass filter. And it converted the FM signal, which is moving back and forth in frequency, to amplitude modulation, which is up and down, and then envelope detected. And then you can recover the signal, which I did here with a direct envelope detector. Only this was a modified version of the problem where I did the complex envelope, but same kind of an idea. And there's the signal right there. One was with the envelope detector, and the other one was with the complex envelope. That's this was the input. This is the output. So, does that sound reasonable? It's kind of a fun problem. It could be a DSP algorithm too. It doesn't necessarily have to be an analog filter like it is in here. It could be something else you're trying to get a slope off of that you can use as a discriminator. And remember, we went through this in class earlier in the lecture notes, this was kind of a low-cost way of making a discriminator, and it works well for narrowband FM, where you don't have to have a really wide discriminator operating point, because it's not going to be that good if the deviation in here gets too big, then you're going to fall off on this gain slope, and you're going to start introducing harmonic distortion. It's gotten really quiet, so I guess I should move on. Go ahead and start thinking about it. Like I said, there's no one right answer. I want you to be creative, and as long as you can justify what you're doing, I don't have a problem with it. Let me just do one last thing, since you might be saying, how do we know it is good or not good? So one of the things I could do down below here is I could generate a longer vector, so I can do some spectral analysis on it. So suppose up here I decide to make 100,000 samples, and then don't really need to do the spectrum again, and then I go ahead and go through the envelope detector, and I'm using the complex one again, but it's just for an example. So I'm using the complex baseband form. So I've got a lot of cycles in there now, but now what I can do is I can use PSD on that signal. I'll use PSD on this one since it's handy. And I want to skip that little bit of a transient that's in there because it's going to mess up my spectral analysis. So I'm going to just try skipping the first 100 points and then go all the way out to the end. And then I'm going to set the number of points in the FFT to 1024. I'm going to set the sampling rate at whatever I picked up above here. I don't remember what I picked. I picked, FS was defined a ways up here, 50,000. So FS was 50 kilohertz. And it looks pretty pure, but it looks like I need a little bit more resolution. So I'm going to go 2 to the 14th. And then I'm going to limit the y-axis so I can just see things that are close in to the minus 19. So I'm going to go from about minus 80 up to minus 5 to see how that looks. Okay, so now I'm going to have to zoom in on that. And the y-axis too. So I'm going to go 0 to 6,000. Okay, so what was the frequency I was using? I thought it was a kilohertz, but I guess it's not a kilohertz. It's pretty tiny. It was 100 hertz. I used 100 hertz. So I'm going to increase that to double that, so the spectrum's going to get fatter. And then take that down here. And I'm going to take a look at this again. I guess I don't really need to do that because I have the equations right in here. And what happened? What changed? I still have my 100 hertz right here, but now I'm starting to get a little bit of a third harmonic. And there's a tiny second harmonic too, but I've got a little bit of a third harmonic. So what's going on here is that because the slope is not a constant in here, I'm starting to create some harmonic distortion because I'm not converting frequency to voltage in a linear fashion. So that non-linear transfer of frequency to voltage starts to create some harmonic distortion. So that kind of limits the ability to make the bandwidth too wide without getting harmonic distortion. And if it was FM broadcasting, you wouldn't want to introduce too much harmonic distortion because that would make music sound not so nice. But this is still pretty good because it's down about 20 dB right now. It's still fairly, well, it's down more than 20 dB. It's down maybe about 35 dB. 20 dB per division, so 20, 30, about 35 dB down. But to show how rapidly it changes, since I built all this up right now, it'd be really easy to just bump this up to peak deviation of 300, and just the bandwidth is now going to widen out more, so it's going to be deviating more. These are the types of things you would have had the opportunity to play with in the lab too, if you were doing the Lab 5 on campus. Now the harmonic distortion has come up significantly. Good. It's so quiet, but I'm going to move on. Go back to phase lock loops right now. That's why I like this problem, though, because I'm a tinkering kind of a person, and I want to encourage you to kind of investigate things like that when you work problems. So this is more or less a design problem. So phase lock loop is going to be useful as FM demodulator as well, and it is not perfectly linear when you use a sinusoidal phase detector. But the linear phase lock loop model that we'll look at will be perfectly linear. It's just not representing the real physical system unless the physical system had a certain type of phase detector that would be linear. So this was the block diagram we looked at last time. Key elements of the phase lock loop would be the phase detector, loop filter, a loop amplifier, which can be integrated with the loop filter, and then a voltage-controlled oscillator. A very practical type of phase detector for phase lock loop is a multiplier. And this could be a double balance mixer like those of you in the lab worked with. Could be a true analog IC multiplier, or if it was a software-defined phase lock loop, then this would just be the multiplication of two discrete time signals. And that is certainly an option today with modern software-defined radio type stuff. So the received signal is going to be a cosine with some phase modulation or phase phi of t. The VCO is a sine, and remember last time I talked about the reason why we pick cosine and sine is that the loop is going to lock when the signals are in quadrature, because when you take cosine times sine you get my pen working again. You're going to get 1/2 sine of sum plus sine of difference. And we're interested in the difference in this case. And the reason why we want the sine shape is that is when the sine of the difference goes to 0, that is going to be when the loop is right in the center of its lock range. So we need a sine-shaped curve rather than a cosine-shaped curve. And this has to do with feedback and control, which I'll be explaining more as we go through this. So when we form that product, we're going to get the two sine terms there. We're particularly interested in the difference, and we're going to assume that the double frequency term or the sum term is removed by some sort of a filter, typically the loop filter, but maybe there's an extra filter. If it's at a high RF frequency, then you can have a small termination filter in the RF domain when you're extracting out the difference term. So we're going to assume that what comes out of that phase detector is just the difference term phi minus theta, and our intent is to make and the loop locks up, that theta of t will follow phi of t. So it's going to be exactly like in a feedback control system where you're trying to track something. So it's a tracking loop is what it's also referred to as. So the voltage controlled oscillator is going to try to get on board to follow through this feedback mechanism the input phase deviation. And what's really special about the phase lock loop is when the signal arrives at you, you just can't reach inside the argument of the cosine and pull out of there phi of t. You have to get it out by some means, and we've already looked at how in the discriminator we were differentiating and getting it back that way through the chain rule of calculus. But we're going to get it directly by the phase lock loop, because the phase lock loop is going to be able to track on that phase difference in the arguments of the sine and the cosine. So we have put the components together. We went through part of this last time. We have the VCO gives an output that's proportional to the input voltage EV, and the gain constant that controls that is the VCO gain constant KV. Lab 5, you would have characterized a function generator in the lab to find out what its KV is. It also puts out a quiescent frequency. So this is the quiescent frequency of the VCO. And what was I thinking of? Well, I was looking at an article I got from Texas Instruments on a new RF synthesizer chip, and they were talking about the tuning of the VCO that's on board the chip and the use of varactor diodes and switched capacitors and so on, which some of you that are into that stuff would be really familiar with, how you might have capacitors that you can switch in and out in an analog IC to be able to control things. At any rate, the quiescent frequency would, in an analog VCO, would generally be set by a tank circuit, and then there's the C that controls the tank circuit, or the resonator for the oscillator, has also got a varactor diode, a variable capacitance diode that can be used to tune it, and that is under the control of the control voltage. The control voltage comes in and changes the bias on the varactor diode. The varactor diode is designed to have a doping profile that hopefully gets a fairly linear tuning curve out of the VCO. That's kind of another story unto itself, but there's other ways of making voltage-controlled oscillators, but in the analog domain it's usually some sort of a resonant circuit and then a tank that has a voltage variable capacitor. So the relationship, just sort of ignoring the quiescent frequency, is that quiescent frequency omega naught is actually going to serve, going to be taken care of up here to match the center frequency of the signal that arrives. So all the VCO has to do is tune about that operating point, and then it can try to follow the input phase and frequency deviation. So the relationship is the instantaneous frequency deviation is proportional to the control voltage times KV, or integrating both sides, the instantaneous phase deviation is KV times the integral of the control voltage. So we now drop that into the phase lock loop block diagram with this math representation, KV times the integral of what's going in, and then gather up some of the gain terms that were included in here. Those three terms came about: trig identity, amplitude of the input, amplitude of the VCO, and then finally the conversion inside the phase detector of how it produces an output that's scaled from the input with some additional scale factor. Oops, my finger tapped a little bit too incorrectly. which always seems to bother me. It happens when I'm least expecting it. At any rate, so that's where KD comes from. So now we've got what's known as a nonlinear feedback control system, and that's because of the sign nonlinearity. The phase detector, in this case, is a sinusoidal phase detector, so it imparts that sinusoidal nonlinearity. When you take feedback control systems, and Chris, you did that last fall, you generally didn't have any nonlinearities in your loop, right? So we're going to get rid of that nonlinearity under a small signal approximation here, but first we have to understand how the phase lock loop deals with that nonlinearity in terms of locking up, and then once it's locked, we can deviate around a stable lock point and then assume that the sign of the phase error, which in this case is psi, that if psi is small, then the sign of psi is approximately psi. So we'll be doing that shortly, and then we'll have a linear feedback control system model. But initially, we want to keep all this together so that we can see some of the idiosyncrasies of the phase lock loop. So we group all of these gain constants together just for convenience. The author calls it KT, as in the total gain all the way around the loop, and it has units of radians per second. When all is said and done, if you look at how the units are defined. So now we can start writing the equations. We can say that theta of t, which is the phase coming out of the VCO up here in this block diagram, this is also a baseband model, baseband loop, because we no longer have the cosine of omega c phi of t and the sine of omega c theta of t present. We just have the baseband signal components phi and theta, which, remember, we can't put our hands on those because they're inside the arguments of the sine and the cosine. But for math modeling, we can still do this, and we can create a simulation model from this too, and that's what I have in Python. So we can write theta of t is kt, which is the all the way around the loop gain, times the sine of the phase difference. And initially, remember, the model is no loop filter. So we're going to use a straight-through connection or unity gain and unity gain amplifier. We're going to have no loop filter. So the loop filter, if it's got an impulse response of delta of t, just means it's a wire. Signal goes straight through it. So that's the closed loop representation of the VCO phase output theta in terms of the input and the sign nonlinearity in the loop gain. Differentiate both sides, and then we have a differential equation rather than an integral equation, and this is what we're going to work from to understand how the loop locks, this differential equation. So this is a first order nonlinear differential equation. If we could get rid of the sign, we'd have a linear differential equation. We'll do that, like I said, in a little bit, but right now we're going to stick with the nonlinear differential equation. It's first order. Make this substitution. Psi is phi minus theta. That's just the action of the phase detector. And then consider that we're going to input a frequency step. We're going to make the input frequency through the use of phi of t jump by delta of omega radians per second. So that is this right here. So d phi dt is going to jump by delta of omega radians per second. So now we go back to the equation up above, trying to use colors here to make sure you're not going to get too lost. Keep that in place there. And now what I'm going to be doing is rewriting some things. So in order to get this term right here, what I'm doing is I'm saying, and this is unfortunately confusing, but I'm saying if I take what's right here and rearrange it so that I have it in terms of theta is going to be equal to phi of t minus psi of t. Then I take the derivative of theta with respect to t, and the derivative of d phi is delta of omega, and then minus the derivative of psi of t with respect to t. And that's going to be equal to what's on the right-hand side up above here, kt times sine of psi now instead of phi minus theta. So now we've just got one variable, and now the focus shifts to this differential equation under the influence of a frequency step. So now what we do is we plot. We're going to change things around a little bit more. We're going to plot d psi dt versus psi of t. So when we rearrange that, we're going to have, clean that up a little bit. Is going to be equal to delta of omega minus kt sine of psi of t. And that's what we've got plotted down here. So vertical axis is d psi dt, the horizontal axis is psi of t. So in order to plot this response for d psi dt, we have to take delta of omega, which you see right here, and then subtract from it sine, kt times the sine. And that kind of makes sense right here, because it looks like we have a sine turned upside down with an offset on it of delta of omega. So right at t is equal to 0, we're sitting at operating point B. Just before we're at operating point B, though, we actually are starting right down here, and as soon as the step turns on, it immediately pushes this characteristic up because this is now active. So it pushes it up, and the loop is now not in a stable lock point. It's sitting there thinking about what it needs to do to recover from that frequency step, because it's kind of like it was standing there balancing, and now it got pushed really hard by that step, and it's kind of about ready to fall on itself, or it's knocked out of lock by that frequency step. So it has to respond to that. So this is the equation, or the way I've been plotting it. I actually moved this over to the other side, right? So then I make some observations. I say, since dt in the world of time moving forward is always positive, so a differential increment in time in the physical world is always positive because it's increasing. If dt is since dt is positive, if d psi dt is positive, in other words, we're sitting above the axes, the horizontal axes, then that means since dt is positive, d psi must be positive. So if d psi is positive, if I'm sitting right here, I'm going to move in this direction because of the fact that that's what the loop equation says I should be doing if what I say here in this statement is true. So I'm going to change colors and talk about since dt is always positive, now if I also say d psi dt is less than 0, so I'm sitting below the horizontal axes, as if I was sitting right in here, then I'm going to have psi of t be negative. So what we established by this reasoning is that the loop is going to try to seek out the place where d psi dt equals 0, because it's always going to want to push either left or right on this characteristic curve, and this is known as a phase plane plot, which is the solution to the differential equation, which vaguely you might remember when you took differential equation, some discussion about a phase plane plot or a phase portrait or something like that. Does anybody remember that? Just curious. Okay, it's okay if you forgot it, because things like that are something that you don't use very often, and so you forget them. At any rate, it's seeking out to go to A. So it's seeking to get to this stable point right here. This is going to be the stable lock point. I wanted to color that or circle that in red again. So it's going to want to sit right there. And another stable lock point would be over here. And as this comes down, there'd be another stable lock point here. This point, oops, I never can get my pen to change when I put my finger. Those 2 points are not stable lock points, because if we're above the axes, like we're sitting right up in here, then what the logic we were going through said we're going to head in that direction. If we're negative, then it says we're going to move to the left. We're going to move in that direction. So the loop is repelling away from those type of zero crossings where the slope is of the opposite polarity. And it's like poles of a magnet. You know, the 2 poles are the same polarity, so they repel, but where they attract is where the slope is coming down negative in that fashion. And that's the nature of the phase lock loop. It's going to have a stable lock point, and then it's going to have unstable lock points. So it's going to gravitate towards a stable lock point. But if I move my mouse around in here, it doesn't have to be this one. It could slip around and end up over here, because if the loop was starting way up over here, it's not going to want to climb up like that. Instead, it's going to, well, never mind. It is going to go in this direction. Depending upon where the unstable point is, it's either going to move towards to the right, or if it's in the opposite side, like if it's sitting, I guess it has to be sitting down here, it will climb backwards and lock up there. And I've got pictures of this. The book has pictures of this too. And another aspect of the phase lock loop is when it does lock up, it's going to have this steady state phase error. So this is what's called static phase error or steady state phase error. And the reason why that is in the first order loop, there's only the integrating action of the VCO, and that is going to be used to convert frequency to phase. And we have to have an error signal present in the loop in order to generate a control voltage that can actually tune the oscillator to that higher frequency with delta of omega needed to track it. So that's this discussion right here. In steady state, the phase error is psi SS. That's because for the loop to lock, the phase plane curve must cross the psi dt equals 0 axes. So the maximum steady state value that the loop can handle is when we get right down to the bottom, and this was to move up and be the zero crossing. In other words, delta of omega would shift this curve up by kt, or delta of omega would be negative and shift the curve down, so the positive peaks here would be down at 0. So that forms what's called the total lock range. We can move the input frequency above or below the quiescent frequency omega c by kt, so the total range is twice kt. And that's called also the hold range or hold-in range for the first order loop. If you know what delta of omega is and what the loop gain kt is, then the inverse sign, because of the characteristic we're looking at in the phase plane, that is the steady state phase error. And that's what the last homework problem has you play around with, just find out different values of steady state phase error. And for this type of phase detector, we have this relationship. The max is plus and minus pi over 2. Since you can't get any bigger than that without the loop breaking lock and never finding lock, and I'm going to demonstrate that here in a second. But if you push this up so far, then if you push it up above that, so the loop phase plane never goes through the 0 axes, then the loop just slips cycles. It madly is trying to slide one way or the other to try to get a stable lock point, but it can't achieve that if the input frequency gets too large. It's outside the lock range and it slips away. Now we're going to go to the linear model though, and I'm going to go do a little example, but first I want to go through the linear model. If KT is large and the error is small, then we can approximate the sign of the phase error as being just the phase error itself. So then we get this wonderful looking S-domain model because we can replace the integrator by 1 over S. The nonlinearity is now gone, and we just have this first order feedback control system. So we have in the S-domain, and that's what this is, so we had phi of t out here, and then see if I can get myself to draw some script as in the Laplace transform. So that's what that is, and theta of t is Laplace transform of, or theta of s, capital theta of s is Laplace transform of theta of t, and then this was kV times the integral with respect to time, and then take the Laplace transform of that. This was a d lambda, let's say, then we get a 1 over s for that integral. So now that we have the linear loop model, we're assuming we're in lock for the loop model to be valid, so we have the error very small. Then we can analyze the loop to perturbations of, say, the input and just see how the response changes. So we can go to the Laplace, we can work in the Laplace domain, and then we just have to manage our way around a block diagram. And I'm thinking you saw some block diagrams in 2610. I'm thinking you see more block diagrams with S-domain stuff in 3205. Does that seem right? Those of you that just had it last semester, didn't you do some things with block diagrams in that class? Okay. So you're familiar with this idea of solving around a block diagram. So here, and this is kind of personal taste thing, but I'm going to start here. I'm going to say I would like to get theta of s. So I write that down. And then I just say, okay, what is theta of s? Well, theta of s is going to be the gain all the way around the loop, because that was this gain and this gain. So that was kt, and then the s coming through this block. So I'm coming around like that. I pick up all those gains. I pick up the loop filter, and the S domain is f of s. I pick up the amplifier mu and everything. All that's lumped together into kV. The constants were, and then the 1 over s from the integrator, and then the loop filter f of s. And what's driving that is this psi of s, which is the phi of s minus theta of s, because that's what's going on here. Notice we have a plus sign and a minus sign. So that is that expression, but then to actually solve for the transfer function, we just pull some algebra on this, and I bring all the theta stuff onto the left-hand side, and I leave my pen starting to freak out here. I leave the phi on the right-hand side. So that's what I've done in the next line. I just have the theta terms on the right. So I have 1 plus kt over s times f of s, and then I have kt over s times phi of s times f of s on the right side. And then finally I can form the ratio of theta of s, which is the output over the input. And I have this form right here, which is a fundamental expression that you find in feedback and control, actually. So we have kt times f of s all over s plus kt times f of s. And this could be rewritten too if you wanted to. How could I write this differently? I could write this as, if I wanted to, my pen is not working on me consistently. And then I could go further and I could say, in some books, like my phase lock loop notes that I've been teaching out of this semester, I had the open loop gain around a closed loop system, called it G naught of S, so I could make a substitution. That would be f of s, kt f of s over s. And then I could see something that you'll see in control systems, that h of s system function would be G naught of s over 1 plus G naught of s. Right, Chris, since you had this class last semester? That's okay. I was just asking if you remember the expression for a closed loop system in terms of its open loop as being G naught over 1 plus G naught of s. Yeah. Well, we do have an integral in here, so our G naught of s has one integral at this point, but we'll go up to a second order loop eventually. So this is a first order loop. When we actually plug those values in for the first order loop, which is what we studied just above the page in the nonlinear form, f of s equaled 1. So this is the closed loop response for the first order loop, and it's a low pass filter. Pretty easy to remember that the loop gain sets the cutoff frequency in radians per second. So cutoff frequency in hertz is going to be kt over 2 pi, but the loop has a low pass kind of response. So we could actually do some analysis on this, and the next bit of analysis I'm going to do is I'm going to suppose that we have an FM message signal out there. So m of t on our input signal is a u of t, and then that goes through the integrator in the FM modulator, and this is going to be what in the S domain? It's going to be a over s, right? Laplace transform both sides. And then when I send it through the integrator in the modulator to form the received signal, I'm going to send it through another integrator, which would be S. So, and then it would have the deviation constant. So that's how I get that set of equations: one in the time domain, and one in the frequency, and one in the S domain. So now we can study what is going to be the output of the loop when we drive it with a frequency step. So I'm going to take this expression right here. I'm basically saying theta of s, and I don't know why I skipped this step, would be psi of s times h of s. And then I make those substitutions. I will have I will have this piece that's from the input right there. Frequency ramp. A frequency step looks like a phase ramp. That's the AKF over S squared. And then the KT over KT plus S is from the closed loop transfer function. So that's the VCO output phase. Now, if we wanted to look at what the control voltage is, so we'll go back up to this block diagram. If we want to back up and take a look at what that is, all we have to do is what? If we know what theta of S is, we can get EV of S to be what? S over KV times theta of S, right? When we're sitting in a system block diagram, we can move around to different points and just take a value that we know, like theta of S, and just back up to the other side of that KV over S, which is the VCO, and that would just be S over KV times theta of S. Make sense? So I do that down here, and I say that the output voltage, get that to go away. Oh well, got to wait for it to go away on its own. Okay, EV of S is going to be S over KV times theta of S, and then just plug in my constants, and one of the S's is going to cancel that I had up above. So I'll have A KF over KV, and then KT over S times S plus KT. And then I can solve in the time domain by doing a partial fraction expansion on that. And I will get something that is going to be like, oh, that makes perfectly good sense to me. I'm going to put in a frequency step, and the VCO control voltage is going to be a step response of a first order low pass system. So we're getting this exponential charge up action on the control voltage, because the control voltage is pushing into the VCO to make it follow the input frequency step, but because the closed loop is a first order response, it's picking up that characteristic of the charge up. And this is just a generalization of that. If it was any type of message, we could put in its Laplace transform and then see that it's going to get shaped. The EV signal is going to be the input FM modulation shaped with the first order low pass filter. So this is LPF filtering of the first order PLL on the control voltage. So the control voltage is following the FM modulation, and that's excellent because we can't get our hands on theta of S anyway, but we can touch the control voltage in a phase lock loop because that's an actual signal that's driving into the VCO. We can't put our hands on theta of S because that's in the argument of the cosine waveform. So I have that built up here. And yeah, this last statement is that for low enough frequencies, it looks like that the control voltage is exactly proportional to the message. It's only when you get up close to the cutoff frequency, the first order low pass, that it starts to drop it down. So we're pretty much out of time, but I'm just going to repeat a little bit of simulation work. I have a simulation function in Scikit DSP-Com called synchronization. It's called PLL1, and it just has this all wrapped up into a package for a baseband loop where you put in modulation. The notation is not following the book, unfortunately. I call it theta. It should be phi, but it is the input phase deviation. Set a sampling frequency. Tell what type of loop you want. We've only discussed the first order, but we will look at second order loops. Say what the KV is going to be, what the cutoff frequency Fn, it's also going to be known as the natural frequency for the second order loop, what the damping is for the second order loop, and then whether or not you want the nonlinearity. So I have that right in here, and this was an example I went through last time where I had a phase step going in, or phase ramp actually, because it's got this T in here. So this is a frequency step of 8 hertz, turning on at T is equal to 1/2 second, and then switching with a minus 12 hertz negative step at 1.5 seconds. So I build that signal up, send it in to the phase lock loop, set the sampling rate at 100 or 1000 hertz. The gain of the loop is going to be the cutoff frequency is going to be 10 hertz, which is the same as the gain in hertz. Kt over 2 pi is going to be the gain of the loop in hertz. So you see that it's following this first order response. The control voltage of the VCO is rising up with this RC charge up factor. It hits 10, or hits 8 and then it comes across, holds there, and then at 1.5 seconds it dives down by minus 12 hertz to net out a minus 4 hertz. And if I was to make that frequency be, say, 2 hertz for the loop's bandwidth, the loop is not going to lock because I'm outside the lock range. I've got to stay within the lock range, which goes up to 10 hertz. So I just did something that I can't really do. I'd have to make this, say, 8, and then it might stay locked. Yeah, it's staying locked there, just barely, because the lock range is going to be plus and minus 8 hertz. But the point I was trying to make is that the time constant now is bigger because the cutoff frequency is lower, so it takes longer to charge up. Whereas if I was to make this go up from, I started at 10 faster, if I was to raise this up to 100, then it's very fast, and I'm running at a loop bandwidth that's too wide relative to my sampling frequency, so it's starting to look like a second order loop. So if I wanted to really do justice to this, I should change the sampling rate to, say, 10,000, and then that problem would go away. And I'm just seeing that it has a very fast rise time, but it's not 0. It's controlled by the loop bandwidth. And then if you wanted to kind of get a better understanding about the phase plane, what we were looking at earlier, I'm just going to take this back to where it was. Otherwise it's going to upset the rest of my examples in here. What I could plot here was, I'm going to plot psi of t. And then I can plot the phase plane plot by taking the derivative of psi and plotting that versus psi. And again, because I'm using the diff function to approximate the derivative, I'd take one less sample out of that. And this is the phase plane plot that we were looking at earlier. So the green dot is where it starts. It comes up here, and it hits a pi boundary. So what it's actually doing is just modulo piing itself, and it's coming back again, and it's finding the stable lock point. What I had to do in this simulation was turn on this argument here. That last argument controls whether it's a nonlinear loop, and when I have it set to 1, then the loop is nonlinear, so it has the sign nonlinearity. I'm looking at where I have that in my help here. 0 linear, 1 is nonlinear. So you can also observe the nonlinear differential equation characteristics. If I make the step too large, like here I'm making the first step 12 hertz and my loop gain is only 10, then for looking at the phase psi, it's just slipping cycles like crazy. It cannot find a stable lock point because it's too high. If I look at it in terms of the VCO control voltage, what I'm seeing is that the loop is trying to rise up and find the input at 12, but it can only get to 10, and then it just thinks I'm gonna pass this by and try sweeping back, trying to go in the other direction. And then it comes up and tries again, and it fails over and over and over again because the lock range doesn't allow it to lock with a 12 hertz step at the input. As soon as I get it close, though, then it will be able to lock. If I bring this down to 10.1, let's say, you'll see that it comes. Let's see, I did that wrong. This keyboard always fakes me out because the keys are so close together. 10.1. It's getting close, but you're seeing over here, it still comes up and it just can't cross through 0 in the phase plane plot, so it's just failing. And if I was plotting this, I guess, yeah, the phase plane plot is failure. It never can find a stable lock point, because notice it needs to sit like right in here, and that doesn't actually touch 0. So it just keeps searching. But as soon as I get the input down, if I set it at 10, it will lock. If I set it at 9.9, it's even a little bit more comfortable. So here it comes up and locks right in. That's in the phase domain, and that's going to show you the static phase error. But here it's locking right at 10. And if I go back and look at my phase plane plot, I'll see the same thing happening. I mean, I'll see that it's finding a stable lock point. These things take some getting used to, and right now we're going to do more of this on Thursday. I've got a demo appointment for my real-time DSP class, and then another demo appointment at 5 o'clock. So I've got to switch modes here. But you've got some things to work on in the homework problems, and then we'll be continuing to study more on phase lock loops. We'll get into the second order phase lock loop, and then we'll eventually look at some tracking characteristics with platform dynamics, like velocity and acceleration and the derivative of acceleration, and how loops respond to that too. That's kind of interesting for SATCOM people. I'm going to sign off, though, and I'm going to stop the recording. I'm going to stop the recording now.